Okay, we're going to continue on here with gases. And last time, obviously, we talked about a number of gas laws. And we have our Boyle's. Well, P1 V1 equals P2 V2. We have Charles. Well, V1 T1 equals V2 T2. Remember, as we talked about, pretty much anytime you're dealing with temperature and a gas law, it does need to be in Kelvin. So again, that should just be sort of an automatic. If you're doing a gas calculation, always convert it to Kelvin. It needs to be in Kelvin pretty much in every gas law. So make sure you do that conversion. There's also Guy Lusik's P1 T1 equals P2 T2. We saw Avogadro's, which is V1 N1 is equal to V2 N2. Sort of putting together all those gas laws gave us the ideal gas law, which is our PV equals nRT. Remember that this one here is the most restrictive in terms of units. Pressure does need to be in atmospheres here. Volume has to be in liters. Moles should obviously be in moles, and T should be in Kelvin, like pretty much all other gas laws. R is our gas constant, which is a value that you always have available to you. And as we talked about last time, uh, they very commonly will not sort of even mention the gas law or give you the gas constant or the gas constant in a problem. So it's just, again, a value that you sort of always have to it. I use, again, the 0.08206, but a lot of books and stuff will nowadays round to sort of 0.0821. So either one is perfectly fine to use. It is also different than the previous ones, as it's no kind of before or after situation. You pretty much just have one pressure, one temperature, and so forth. We got to the combined gas law as well, which is our P1 V1 T1 is equal to P2 V2 and T2 in this particular case. And same thing here again in all these temperatures, wherever temperatures is, it does need to be in Kelvin. Obviously, the rest of the units can really be any unit you want as long as they basically are the same on both sides and everything sort of cancels out in terms of their units. Now, again, there's a number of gas laws you are responsible to know, but as I mentioned before, really these two that I box here, pretty much if you just remember those two, you really could get any gas law that you would need. Um, and again, if you want to remember the sort of version of this with the moles in it, you can as well. And basically, as we talked about last time towards the end there, uh, if you remember this sort of combined gas law, really all you have to do is scratch out whatever is not in the problem, not given to you, held constant. Again, if you had no moles or temperature given to you, as we talked about, you pretty much could just scratch it out. And then now you have pretty much Boyle's law there. Again, anything that is not given to you, not in the problem, all you have to do is scratch it out. And then you'll have pretty much the right gas law to use. Again, no pressure or moles. You just scratch those guys out. And now, again, you now have basically Charles' law given to you. So it's a really good one to sort of remember. And again, just take out whatever is not given to you in the problem, and you'll pretty much have the gas law right in front of you. So that really does sort of cut down on what you need to remember. Again, if you just focus on the ideal gas law in that one there, you should be in good shape again in terms of determining those gas laws. Remember as well, we talked about rearranging these. It's oftentimes problematic for a lot of people. So again, just keep it very simple. If we go across the equal sign or move something to the other side of the equal sign, it does end up in the opposite location. So just go opposites and you can rearrange the equation probably pretty quickly as well. Any question on any of those there? Okay. So next couple of things we're going to talk about in terms of gases is how to calculate the density of gases and the molar mass of a gas. And these are two ways that you could do it. I will say, and as I'll mention and sort of show, really they're kind of based off of the ideal gas law as well. So when we talk about density of gases, as we talked about earlier, usually the units that we are looking for is usually grams per liter in terms of gases, and rather than grams per milliliter like we typically see for solids and liquids. And the density is mass over volume, which this is an equation for a gas to calculate. That's the pressure in atmospheres. That is the molar mass in grams per mole. That is the gas constant, and that obviously is our temperature in Kelvin. So the density of gas is equal to pressure times the molar mass divided by R and divided by T. So you can also, in that particular case, sort of, if you don't want to remember this equation, or really even the bottom equation here, so let's take a look at that one first. Molar mass of a substance is grams per mole, and those are the units for molar mass, and that's equal to the density in grams per liter. R is the gas constant, temperature, and obviously our pressure there in atmospheres. So this is the way that you could calculate either the density of a gas or the molar mass of a gas. So again, if you don't want to sort of add two more equations to your list of things that you have to remember, you really could still get to these through the ideal gas laws. For example, PV equals nRT. And for example, if we were looking at density and we wanted it in grams per liter, we could actually take the ideal gas law and solve for N over V. And if you do that, you're going to divide this side, take these two guys back to the other side, and that will give you basically P over RT. And if you think about the units associated with N over V, N is moles and V is liters, and that is the molarity. Yeah. So that's basically the molarity of a gas there, moles per liter. So if you do this, what you're going to end up with in terms of units will be moles per liter. And really you need to get to grams per liter. So that is the molar mass that you would use in that case. And the molar mass, moles will cancel and you'll end up with grams per liter. So you can get to these formulas through the ideal gas law. Pretty much that is this part right here. And then you're going to times it by the molar mass, which is that part right there. So if you can't remember these, you could derive it basically from the ideal gas law and just approach it as really just like a kind of unit conversion type thing. Get rid of the units you don't want, keep the units you do want, and that's a really good way. Same thing down here. For example, if you're looking for the molar mass, which is in grams per mole, typically in these problems, they will actually just give you that number right there. So they'll oftentimes just kind of give you the grams of your gas somewhere in the actual problem. So really the only thing you need is moles, and that also could come obviously from the ideal gas law. And you solve for N, which is PV over RT basically. And then you would have the moles part of it. So both of these equations essentially are really derived from sort of the ideal gas law. And again, in a situation like that, you can just think of it more as like a unit type of dimensional analysis type of problem. And you could kind of use the ideal gas law to solve for both the density or the molar mass. Or you could just remember those formulas as well and plug and chug into there, whichever way you want to do it, it'll come out basically the same. Any questions on that? Again, you do have to be careful, obviously, as I mentioned here, unit wise, you do want to make sure everybody's in the proper units so that everything does cancel out correctly. All right, so let's try one here. A 2.1 liter vessel contains 4.65. Let's take a look. Once again, like I said, you can plug and chug into these formulas here. But again, I'm just going to take the approach of maybe I can't remember those formulas. So I'm just going to think of it more as like a dimensional analysis. I'm just going to try to get to the right units type of approach. First thing I know, hopefully, is molar mass units are grams per mole. So when we go through this, we obviously have a volume, which is 2.1 liters. We have grams given to us. So we do have that number, which is 4.65 grams. So we got half of what we need already. We have a pressure of 1 atmosphere, and we have a temperature of 27 degrees Celsius. So as I mentioned before, we could always kind of go back to the ideal gas law here. I got a volume, I got a pressure, I got a temperature. I always have R even though it may not be given to me. So once again, 206, there you go. I can solve for moles, which is actually the last thing that I do need to get to the molar mass. So again, this is sort of how you might want to think about it. In terms of the units here, we're all good in terms of units, except for obviously, like normal here, our temperature does need to be converted into Kelvin. So we'll add our 273 to that to give us 300 Kelvin. So now we could solve for N here, which is our moles. We're going to divide this to the other side, gives us PV over RT. So our pressure will be 1 atmosphere. Our volume here would be 2.1 liters. And divided by 0.08206 liters atmosphere Kelvin mole. And we have 300 Kelvin there. All right, so atmospheres cancel, liters cancel, Kelvin cancels. We got moles on the bottom, but when we divide, it'll come to the top, and we will end up with basically 2.1 divided by 0.08206 divided by 300, going to give us here 0.0853 moles, which again is the bottom part. So what's left now is just the molar mass would equal our 4.65 grams that was given to us, divided by the moles that we use the ideal gas law to get. And that is going to give us a molar mass here of about 54.5 grams per mole. So again, as I mentioned, just kind of take it as a more conversion problem. Sometimes it's a little bit easier than maybe adding on another equation to sort of remember. Any questions on that particular one there? All right, let's take a look at another one. Let's try this one. What is the density in grams per liter of oxygen gas at 700 and we'll go 78 torr and 27.5 degrees Celsius? Okay, so once again, let's take a look. We're looking for density, and again, you can either remember the formula or just kind of get to it through what's given. So pressure is 778 torr. We have a temperature of 27.5 degrees Celsius. I know that I could probably get there somehow through my ideal gas law. So I have pressure given to me, I have temperature, I always have R. I don't have N and V, so this is the one where we could solve for N divided by V. And again, we're going to bring this way and these two guys to the other side. And that will give me P over RT. And those guys I do have. And again, because this is ideal gas law, it also reminds us that we do have to watch our units. So we do need to convert our pressure into atmospheres, which is 760 torr is an atmosphere. And if we divide that out there, looks like 1.02 atmospheres. We also, like normal, got to add our 273 here to our temperature, 300.5 Kelvin. All right, so popping this in here, going to get us 1.02 atmospheres divided by our gas constant, 0.08206 liters atmosphere Kelvin mole, and times our 300.5 Kelvin. Doing all that good stuff there, going to get us looks like 0.04136 units here. Atmospheres cancel, Kelvin cancel, moles per liter flip around when you divide it, and we end up with moles per liter, which is the molarity here. That is close to what we want, but we do want grams per liter. So really at this point, it's just a conversion between moles to grams, and that is the molar mass from the periodic table that allows us to do that. So that's going to be 2 times 16 there for our molar mass of oxygen, which is our 32 grams per mole. So to finish it up here, we'll do a little dimensional analysis kind of conversion here. Moles on top, liters on the bottom. We're going to actually multiply by the molar mass so that the grams end up on top. Moles on the bottom and top will cancel, and that will get us to like 1.32 grams per liter. Any questions on that there? So again, hopefully you can see that really, again, both of those sort of forms that we saw earlier sort of derived from and really do come from the ideal gas law. Again, I would take more just like using the ideal gas law in the dimensional analysis approach, or again, you could obviously memorize those two equations and use the equations. Any questions on either of those calculations? All right, then let's talk about some other aspects here of gases, and that is going to be gas stoichiometry. So obviously we've done regular stoichiometry, we've done solution stoichiometry. Why not do gas stoichiometry if we're not have some time here? Much like all other stoichiometry, they're pretty much the same sort of steps. So as we talked about a number of times up to this point, there's really those same four basic steps. You want to make sure always right balance your equation. You got to convert to moles. Again, you're going to do really the stoichiometry part, which is your mole to mole relationship. And lastly, you're going to take those moles to some other unit. So in terms of gas stoichiometry, I would say that pretty much somewhere along the way, you will use the ideal gas laws pretty much most of the time. That's sort of what's going to happen. So at some point along the way, a lot of times at the very end here, we will use the ideal gas law and solve for something like volume of the gas is going to be reduced. So that's a very sort of common ending. Once you get the moles at the very last step, kind of use the ideal gas law. The other place you could actually use the ideal gas law, it does happen occasionally, is up here in step number 2. And usually if you use it up in step number 2, you would be solving for moles. So you could use the ideal gas law kind of up front, solve for moles, and then kind of do the stoichiometry part of it. So much like all other stoichiometry problems, kind of the same steps. Kind of like what we did with solution stoichiometry, where we use molarity and volume, maybe at the second step, last step. Here, we'll use probably the ideal gas law at the first step or last step, or second step or last step there. Also, just like we talked about with solution stoichiometry and stoichiometry in general, you always also want to make sure, you're not in a limiting reagent type situation, which can also happen, obviously, with gases or any type of stoichiometry problem. So if it is a limiting reagent type problem, again, you can apply the ice table, however you want to do it, but you do need to figure out the limiting reagent. I would say probably in most cases, it's going to be more of a basic stoichiometry problem, probably with gases, but you can have a limiting reagent situation that does sort of develop. So let's take a look at one here. What is the volume of CO2 that's produced at 37 degrees Celsius and 1 atmosphere when 5 grams of glucose are in this reaction? So we're interested really in this gas here, which is our CO2. And what we know about the gas is it is at a temperature of 37 degrees Celsius. It has a pressure of 1 atmosphere, and we're looking for a volume. So again, if we just look at our ideal gas law, pressure we're looking for a volume. We do have the temperature, and again, we always have our. So really, the one thing that we're missing in order to sort of solve for what it's asking is the moles of CO2. And that's really where the stoichiometry part of it comes into play. So we need to do just a basic stoichiometry problem to figure out the moles of CO2, and then we're going to go into the ideal gas law. So we'll start this sort of process like normal. We obviously have an equation and it's balanced. It is not a limiting reagent type situation, as we obviously only have one piece of information given to us in terms of our reactants, which is this guy. Step number 2, we do need to convert to moles. To do that, we will need the molar mass here of our glucose, which is 6 times 12.01 plus 12 times 1.008 plus 6 times 16 here. And that's going to give us a molar mass there of a lot, maybe. Let's see. About 180.2 grams per mole. So that's going to be our second step, like a normal stoichiometry problem. This is the only other piece of information that was given to us. We're going to go 5.60 grams of C6H12O6. We're going to use the molar mass. Grams are going to go on the bottom so that they cancel. Moles of the C6H12O6 will go up on top. And if you get an answer at this point, plus you don't necessarily have to, but if you did, you'll get 0.03108 moles of C6H12O6. At this point, we then want to do step number 3, which is the actual stoichiometry part of it. And from the equation, we can see 1 mole of glucose gives us 6 moles of CO2. Again, just the coefficients. So step number 3, we'll take our number we just got there, 0.03108 moles of our glucose. Using our mole-to-mole relationship from the equation, 1 mole glucose gives us 6 moles of CO2, and that is our stoichiometry part. The moles will cancel, and that will get us here basically times 6, 0.1865 moles of CO2. Any question on that so far? At this point, we now have kind of the missing piece that we need to solve this, which is the moles. So now we have our moles here of it, and we can now go into the ideal gas law. In this case here, we're going to solve for volume. So volume will equal nRT divided by P. We do have to do one conversion here. Not surprisingly, it is the temperature. So we do need to add our 273 to our temperature. So 37 plus 273 going to give us 310. Everybody else should be in the okay units here. So putting that in, maybe, go maybe on this page here. So V is equal to nRT over P. So we just got our moles there, which is 1865. 0.1865 moles. We'll use our gas constant 0.08206. I believe our temperature was 310, if I'm not mistaken. And we're going to divide it by our pressure, which I think in this case was just 1, actually. So our atmospheres will cancel, our moles will cancel, our Kelvin will cancel. It's going to leave us liters. And in this case, we will end up with about 4.74 liters would be produced of CO2. That would be, by the way, it would be a theoretical yield here, as it is a product, obviously, in liters. Any questions on that there? So as you can see, really the same sort of 4 basic steps for stoichiometry. The only difference is, again, somewhere along the way, even once or twice, may probably use the ideal gas law. Any questions on that? All right, so why don't you try one here and see. Magnesium reacts with hydrochloric acid, which you'll do next week, I think, this exact one. Through this reaction, calculate the volume of hydrogen gas that should be produced at STP if you started with 5 grams of magnesium. I believe magnesium is 2431. Okay, so let's take a look. What's getting here? Stoichiometry problem. So we're just going to follow our steps here. We have an equation and it's balanced. We are interested in this case in how much hydrogen gas is going to be produced. So we're looking for the volume here. We do know it is at STP, which a reminder is actual values, 273 Kelvin for the temperature. and the pressure is 1 atmosphere when it mentions STP. And in this case, if we think about sort of our ending, we're going to use our ideal gas law probably at the end. We do have the pressure. We're looking for the volume. We do have T and R. Once again, we're going to need to do the stoichiometry part here to get to the moles of our hydrogen gas in this particular case. So to do that, the only other piece of information we have is magnesium. So that is where we're going to start. We're going to do really our second step, which is convert our magnesium into grams convert from grams to moles. It is not a limiting reagent problem or anything like that because, again, we're only given magnesium and it reacts with our sort of excess amount of HCl in this case. So 2431 from the periodic table, going to get us here 5 divided by 2431 looks like 0.2057 moles. Magnesium. We are interested in hydrogen, so the relationship between these two, as we can see from the equation, is a 1-to-1 relationship. So for every 1 mole of magnesium we put in there, we get 1 mole of hydrogen gas out. So that is step number 3, or really the stoichiometry part, which gets us to basically the same number there, 2057 moles of hydrogen. Any questions up to that point there? This again is sort of where gas stoichiometry deviates a little. We're now going to use our ideal gas law here to solve for what we're looking for, which is our volume, which would be nRT divided by P. Putting in our numbers there, 0.2057 moles, or 0.08206 for our gas constant. I'll squeeze it in here, 273 Kelvin next to it, divided by our 1 atmosphere in this case. Kelvin will cancel, atmospheres will cancel, moles will cancel. Going to leave us liters when it's all said and done. And that's going to get us here 206 and 273. Call it 4.61 liters of H2 would be produced in this case. Once again, that would be our theoretical yield as well. Any questions on that there? Now, just like we talked about earlier, this is at STP conditions, which means for the very last step, you don't necessarily have to use the ideal gas law because this is at STP conditions. That is a place where you could use that conversion. 1 mole equals 22.414 liters, which means we could pick it up right about there and we could go 0.2057 moles of H2. We could use that conversion. 1 mole of H2 would equal 22.414 liters. And that should also give us our 4.61 liters of H2. So this would be a situation, as you can see, because it is at STP, you could use the bottom conversion rather than the ideal gas law. Again, a reminder that you cannot use that conversion if it is not at STP. So, but you could always use the ideal gas law like we did on the top part here. So again, just another option as to how you could solve for this particular problem here. Any question on gas stoichiometry? Yeah. We'll add it to our growing list of stoichiometry type problems. Yeah. Again, much like all others, pretty much same deal. Just use a gas law, usually the ideal gas law somewhere along the way. All right, the next thing we're going to talk about then is the Dalton's law of partial pressures. Now, oftentimes we do have gases, and they're oftentimes given to us as mixtures of gases. And when we do have mixtures of gases, that's where we get what are referred to as partial pressures. And it sounds really difficult, but it's a pretty basic sort of idea of what is happening here. So very simply, if we had just a container, for example, that had only gas molecule A flying around in it, the total pressure of that particular container would pretty much equal just the pressure of gas molecule A, as it's the only gas basically flying around. Now, if we had a mixture of gases in a container, say we had gas molecule A, B, C, and that's all the alphabet I remember, but we have all these guys basically flying around, and they each are really going to contribute to the overall pressure of that particular container. So in this particular case, the total pressure will equal the pressure of A plus the pressure of B plus the pressure of C. These are what are referred to as being partial pressures because they partially contribute to the overall pressure, basically. So really all partial pressures is you just need to find the pressures of each of the gases and then basically add them up together, and that'll give you the total pressure that's in that particular mixture. Now, this is where one of those ideas of a gas being ideal comes into play really nicely, which is, as we talked about, one of the aspects of an ideal gas is the idea of there is no attractive force or repulsion type forces between gas molecules when they're in a container together. So even though we do have basically different gases flying around in the same container, we're going to assume in most cases ideal conditions. And what that means is we could almost think of each of these gases being in the container by themselves because all the other gases are not going to have any influence on the pressure of, say, gas A. Gas B and C won't have any influence on that. Gas B's pressure won't be influenced by A or C that's flying around. So in an ideal situation, because there's no real interaction between the different gases, we could almost assume that they're in there by themselves. So what that does is it makes this calculation relatively straightforward. And in most cases, you're going to probably roll with your favorite gas law, which is PV equals nRT. And you're going to solve for P, which is nRT over V. And basically what you will do is basically just do, in my example here, 3 different ideal gas laws where you solve for pressure for each of the gases basically separately. Now, one of the nice things about it, though, is because they are in the same container, even though they're not interacting with each other, that container will have the same volume, and that container is probably sitting in the same spot, which means it'll have the same temperature. So when you look at the ideal gas law in your calculation for each of the gases that are in a mixture, R is a constant, T, V, all these guys for all 3 gases in my example, those values will all be the same for everybody. So really the only thing that's going to be different for each of the gases in a mixture is basically how many moles that you have basically will be the only thing that's going to be different in the calculation. So you're basically going to roll with the same temperature for all of them because they're in the same container. You're going to roll with the same volume for all of them because they're in the same container. And obviously R is a constant, which would be the same same value for all of them as well. So you basically would just, again, like I said, very commonly do a ideal gas law for each of them, add them all together, and then that's going to give you your total pressure of that mixture. Any questions on that there? And that's pretty much what this says. Now, what happens though if we do come across though a situation where maybe you do not have enough information to go into the ideal gas law? And that does happen. So maybe you're not given enough information to actually use the ideal gas law. There is another sort of workaround in terms of partial pressures, and that is a situation where, maybe you don't have the temperature or volume maybe given to you, but maybe you have enough information about the gases in that mixture to figure out the moles of each gas. So maybe you can figure out the moles of each gas. And you have one piece of information about pressure. That could be the total pressure. That could be the pressure of one of the gases, partial pressures of one of the gases. If you have a pressure and you're able to get to the moles of each gas that's in that mixture, you could actually use this equation down here to help you figure out what's going on. That is the partial pressure of a gas is equal to the thing that we saw in the last chapter, mole fraction of that component, and that is the total pressure or the barometer reading. Remember that the mole fraction, as we talked about, is the X, and that basically is the moles of the gas you're interested in divided by the total moles. It's that guy that's like a percentage without multiplying by 100, so not really a percentage, so point something type number. So if you have that type of piece of information, you can definitely still calculate the partial pressures of everybody. You can also calculate the total pressure. So if you have pressure, any pressure, partial pressure, total pressure, and enough information to get the moles, you could still figure out the partial pressures of everybody in a mixture of gases. I will say probably the ideal gas law is the most common way, but again, in a limited sort of information system, the partial pressure is equal to the mole fraction times the total pressure is a good way to go. Any questions on that there? All right, so why don't you try one here? We got 5 grams of helium and 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. What is the partial pressures of helium and neon, and what is the total pressure here? Helium is 4.003 and neon 2018, I believe. All right, so we're looking for 3 things: partial pressure of helium, partial pressure of neon, and what the total pressure would be in this case. So see what you come up with here. Okay, so let's take a look. Again, in this case, we do have a mixture. So we got a container. It's got some helium flying around. It's got some neon flying around. So again, they're both going to contribute to the total pressure, which we know that the total pressure here in this case would be the partial pressure of helium plus the partial pressure of neon. So to do that, we look at the information. We do obviously have a volume. We do have a temperature given to us, which, since it's a gas situation, probably should convert to Kelvin. So we'll do that. And we're looking for pressure. So again, our PV equals nRT. As we talked about, we could solve for pressure is nRT over V. And we're going to do this for each gas. We have the temperature is going to be the same for both because they're in the same container. The volume is going to be the same for both because they're in the same container. R obviously is going to be the same for both because it's a constant. So really the only thing that we're sort of missing for each gas in this case is the moles. So we just need to convert each of these into moles and then go into our ideal gas law. So we'll start with that, 5 grams of helium here. We'll use the molar mass from the periodic table, 4.003 grams per mole of helium. Will give us for helium here, I'll call it 1.25 moles. We'll do the same thing for our neon, which is also 5 grams. So using the molar mass here of neon, 2018 grams per mole. Gonna get us here, I'll go 0.248 moles. At this point, we really have everything that we need for each gas to go into the ideal gas law, as now we got the moles basically of each of them. So we're going to go, like I said, just individually, because of the ideal gas situation here. We could assume that almost like they're in there by themselves. So we'll start with the pressure here of our helium, which will be nRT divided by V. We're going to put in our moles for helium, which was 1.25. We'll use our gas constant. We will use our temperature divided by our volume, which was 2.5 liters in this case. Moles will cancel. Kelvin will cancel. Liters will cancel. It's going to leave us atmospheres, which is good since that's the pressure. 1.25 times 0.08206 times a 300 divided by a 2.5. And we're going to go with 12.3 atmospheres. This would be considered the partial pressure of helium in this case. Any question on that calculation there? Pretty much we're just going to roll with an identical calculation here for neon, except obviously in this case we're going to use the moles for neon that we calculated, and that was 0.248 looks like. 0.08206 being our gas constant. Same temperature again because they're in the same container, and same volume because they're in the same container. Everything's going to cancel out except for atmospheres, just like above. And we will end up with a number maybe 2.44 atmospheres. That would be considered the partial pressure of neon. Any questions on that calculation there? Now, as we talked about earlier, to get the total pressure, we're pretty much just going to add them together. So the total pressure of this mixture is going to be the partial pressure of helium plus the partial pressure of neon. So that's going to be a 12.3 atmospheres plus a 2.44 atmospheres. And that will get us here a total pressure about 14.7 atmospheres. Any questions on that? Major contributor to the pressure in this case is which gas? Major contributor is helium. Yes. Helium is contributing 12.3 of the 14.7 total. The reason for that is, as we will talk about shortly, it has to do with the molar mass. Helium is a much lighter gas, which means it should be traveling a lot faster, which means because it's flying around a lot faster, it will cause a lot more collisions and contribute to a lot more of the pressure. So under these conditions, the lighter gas is going to move a lot faster. And that's why we see a much higher partial pressure for helium than we do for neon. Any questions on that there? All right, let's try another one here. Sample of natural gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. If the total pressure of the gas is 1.37, what is the partial pressure of propane? Okay, so let's take a look. So in this case, we got a mixture of these three gases hanging out. We got a little methane at 8.24 moles. Got some ethane at 0.421 moles. And we got some propane at 0.116 moles. The total pressure of all these gases as they're flying around is 1.37 atmospheres. So we're looking for the partial pressure of propane in this particular case. It kind of eliminates the availability of perhaps using the ideal gas law, as clearly there's no mention of volumes, there's no mention of temperatures or anything like that. But what we do have for each of the gases that are in this mixture is the moles, which, by the way, we could also get if they were given it to us in grams, right? Because we could convert them into moles using the molar mass. So in this case, they already kind of converted it all into moles. So because of that, we could use the other sort of partial pressure equation we saw, which is partial pressure of a particular gas is equal to the mole fraction of that gas times the total pressure. That we do have all the information that we would need in this particular case to do that. So in this case, we're going to calculate the mole fraction here of our propane, which is C3H8. So to do that, that's going to be the moles of propane, which was 0.116 divided by the total moles. So we're going to take 8.24 moles. We're going to add it to 0.421 and add it to 0.116 moles. I think it's like 8.777 if I'm not mistaken. 0.116 divided by all those guys added together is going to give us a mole fraction for propane of 0.0132, or about 1% or so. With that, that is the mole fraction. We do have the total pressure given to us, so we could use this formula for our propane and calculate what we need. So 0.0132 times our total pressure of 1.37 atmospheres. Going to get us here 0.0181 atmospheres as the partial pressure there of propane. Any question on that there? Now, again, you could do this for the other gases as well. You could just calculate the mole fraction for your other gases that are present and use the total pressure as well. So, for example, if we did, say, our methane in this case, it would be the mole fraction for methane, which would be 8.24 moles divided by 8.777, which is the total moles. So 8.24 divided by 8.777, 0.939, which we then can multiply by the total pressure. And in this case, we will end up with about 1.29 atmospheres, right? And obviously at this point, you can do the same thing for ethane, or you could add the 1.29 and the 0.0181 and subtract it from the 1.37, and you'll get like 0.06 atmospheres for the other gases present. So, or you could calculate. We also see kind of what we saw a second ago. Out of all three of these, it is methane, which is the lightest of all three, and it is contributed to most of the pressure in that mixture. Since the total pressure is 1.37, methane in this case is actually contributing 1.29 atmospheres of that. And again, because it's lighter, it's flying around faster, causing more collisions than, say, propane, which is heavier, causing the least number of collisions probably, and 0.01 in terms of atmospheres. And like I said, I calculated ethane just there. It's like 0.06, which is again in the middle of the two. So again, these molar mass, or how heavy the gas is, will affect how fast it's flying around, and that will obviously affect its contribution to the total pressure. Again, the lighter the gas, it should cause more collisions as it's moving around faster. Any questions on that type of partial pressure situation? So we've seen now a couple of types of partial pressure situations, one where you have enough information really just to do the ideal gas law with everybody. Here, you don't have all the information, but you have enough information, like I said, one type of pressure, either partial pressure or total pressure, and also the ability to get to the moles of each of the gases. You can use, obviously, this type of formula. Another very common sort of partial pressure situation that occurs is during experiments when you collect gases. So this will happen, I think, when we do an experiment in one of the cases, in a sense. But very often in the laboratory, when we do collect gases, we oftentimes will collect gases that sort of involve water. So for example, in this reaction, which is a very common experiment, you take some potassium chlorate and you heat it up. And when it does, it goes through a decomposition reaction, and it will actually produce oxygen gas. And you could collect this oxygen gas very commonly by taking a bottle that's filled with water, and you dump it upside down in a bunch of water in a trough or something like that. And as the oxygen is being created, it will basically bubble through the line here, through the water, and the oxygen gas, which are the bubbles, will come into your water container there. and it will displace the water. So the water will go out, the gas will go in. And what you'll eventually see in your sort of collection container is this sort of empty space. And in this empty space, it's really not empty because that is, frankly, in this example, where the oxygen gas ends up. So that's where the gas sort of ends up in your collection thing, even though when you look at it, it looks empty, but it's actually in there. Now, part of the problem, though, when you collect a gas like this, which is a very common sort of way that gases are collected in the presence of water, is as this reaction is happening, there frankly usually is some heat associated with it. And when heat and water come together, in addition to collecting the oxygen gas, which is really what you're interested in, you also get some water vapor that comes along for the ride. So you collect some water vapor with it, and you get really a mixture of gases in this situation because you've now collected oxygen gas in this example and the water vapor. But in reality, when you go do some type of calculation, or the reason for this experiment was really to figure out how much oxygen you collected, not really the water. So the total pressure in this situation would be the partial pressure of oxygen plus the partial pressure of water, which is sometimes referred to as the vapor pressure of water. And it turns out to be a fairly simple sort of calculation. It ends up being really just a subtraction because what you do is, for example, the partial pressure of oxygen, which is what you're interested in, you would take the total pressure minus the vapor pressure of water. And the total pressure, like I said, in the laboratory would be your barometer reading, and you subtract it off. So oftentimes when you do some type of experiment like this where you collect the gas with water being involved, you get sort of water comes along for the ride, and you sort of have to correct it off and sort of subtract off water's contribution to the pressure because again, you're not really interested in the water aspect of it. So in general, in this type of situation, the total pressure will equal the pressure of the gas you're interested in minus the vapor pressure of water. Sometimes when you do this type of situation and you calculate, for example, something like this, the pressure of the oxygen gas is sometimes referred to as the pressure of the dry gas. And they were sometimes referred to as the pressure of the dry gas because you're subtracting off water's contribution basically to the total pressure. So it's a very common thing. The good news is the vapor pressure of water is typically a table value. So you basically just go to a table, you look up the temperature, and it'll give you basically the vapor pressure of water, and then you can just subtract it off and obviously get what you need. Any questions on that? So that's a very common sort of situation that occurs. And there's some keywords that you know it's this type of situation when you read a problem. It will say something to do with water. So it will say the gas was collected over water, or it'll say the gas was saturated with water vapor. So those are all sort of keywords of this is sort of this type of situation. You do have to do this correction calculation to subtract off the vapor pressure of water. Any questions on that there? All right. And here's an example of a table where you could go and look up the vapor pressure of water just based on temperature. And again, it's oftentimes used in laboratories and experiments and really kind of used as a correction calculation to get rid of the presence of water, which you're not interested in. So why don't you try this one? A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31. Okay, so here in this situation is pretty much what we just talked about. We collected this gas over water, so sitting in sort of the empty spot of our collection tube is the oxygen gas. We did collect some water vapor with it, and that's sort of the key word that you will sometimes see in problems, saturated with water vapor. In this particular case, they were nice enough to give us the actual vapor pressure of water at that temperature. If not, a lot of times you do need to go reference a table to find that value if it's not given to you in a problem. In this case, the total pressure would be the pressure of the oxygen gas plus the vapor pressure of water. In this case, our total pressure was 753 torr. Partial pressure of oxygen plus the vapor pressure of water, 31.824. Basically, just going to subtract this to the other side. Gives us the partial pressure of oxygen, or the dry oxygen gas, at about 721 torr. We do want it in atmospheres, so we're going to convert it by dividing by 760, and that will convert it into atmospheres. And if we do that, it's like a 949, looks like 0.949 atmospheres. So this would represent basically the partial pressure of the oxygen gas, again, taking off water's contribution, which if you did this experiment, you're probably not interested in water to begin with. So any questions on that? So those are three types of partial pressure type of situations that you'll come across. One, just got a mixture of gases, have enough information, you go into the ideal gas law and solve for it. One, you have some mixture of gases, but don't have enough information for the ideal gas law, but do have enough information to get the moles and one pressure associated with it. And lastly, a very common sort of laboratory situation where partial pressures come into play. Anytime you collect a gas with water being involved or saturated with water, you do have to sort of correct that pressure calculation to get rid of the contribution of water. Any questions on any of that there? Got. So I think that's a, actually we'll take a look at this here. So we've talked about a number of these things, but the kinetic molecular theory of gases, as we've talked about, gases are composed of molecules that are separated from each other at distance greater than their own, and they're considered to be points, and they must possess a negligible volume. So as I mentioned before, this part of the sort of kinetic molecular theory of gases is one of the main things that we think about when we think about an ideal gas. Again, we oftentimes think about the container itself and the volume itself of the container rather than the volume of the gas. So you can think of it like a little small pebble, a little small guy in a big container. The volume of the container is much more significant than the volume of the gas itself that is flying around it. Gas molecules are in constant motion and direction, and they frequently collide with each other. These collisions are thought to be perfectly elastic. It is those collisions that basically contribute to the pressure that we see. Again, more collisions, more pressure, less collisions, lower the pressure. Number three, gas molecules exert neither attractive nor repulsive forces on one another. This is really the second sort of thing that makes something an ideal gas or behave in an ideal gas situation. And that's really the reason for what we just talked about, which was we were able to do these sort of partial pressure problems, even though all these gases were thrown in there together in the same container. We could almost do the calculation and do the calculation like they were in there by themselves. So the other gases that are floating around in there with them in an ideal situation will have no direct impact on the other gases that are in there and no direct impact on, say, the partial pressure and things like that. So those are the two main points of the kinetic molecular theory that make something an ideal gas. And in most situations under normal pressures and temperatures, we do assume the ideal gas, and why we use the ideal gas law, the PV equals nRT. The average kinetic energy of a molecule is proportional to the temperature in Kelvin. Any two gases at the same temperature will have the same average kinetic energy. And again, as we've seen in a couple sort of relationships, the increase in temperature usually will result in the gas molecules moving around faster. A decrease in temperature typically will result in the gas molecules moving around slower. Any question on those parts of the kinetic molecular theory there? Yeah, I think we will lay it up there for today.